Good evening. Today we will be presenting to you our second and final progress presentation of Thesis 1. We are Group 10, consisting of Omar Radwan, Khloud M Abdelrahman A Abdelwahab, Mohamed T Selim, and myself, Ahmed M Ibrahim. Starting with the table of contents, today we will go through the introduction, our chosen datasets, our implemented algorithm, the generated prototype, the front end of our application, how the process will take place, and what our updated time plan will look like. And finally, our conclusion and references. As a quick recap, COVID-19 has witnessed an abrupt, lightning-quick outbreak in early 2020, which has caused numerous preventable illnesses and eventual fatalities, compelling the world to adjust and attempt to reduce its detrimental impact. As of the current moment, the discovery techniques of the virus are not very time effective, which belittles the extent to which we can fight against it. Therefore, we have come up with our project idea, which is to utilize X-ray scans and image detection methods, together with the aid of machine learning models, in order to produce a rapid decision regarding the existence of the virus. Starting with the project's aim, we have maintained a clear objective for our project, which is the diagnosis of the virus with the highest possible degree of accuracy by collecting images of chest computed tomography, or CT, scans that are retrieved from established databases, and then utilizing techniques to assess whether or not a patient should be designated as a virus carrier. To present our aim in a shortened form, we hope to achieve a concrete method of detecting the virus, which is meant to become simpler in design, cheaper in cost, easier to extract, and wider in access than the other current alternatives available. We have managed to implement numerous advancements in our project in comparison to the last progress presentation. We have done so firstly by coming up with a general abstraction of how our application front end will end up looking like. Furthermore, we have established in detail how our segmentation process will be performed in order to extract a refined image that is perfectly suited for accurate classification. Afterwards, we have allocated our CNN that will perform the classification and carefully decided on the amount of layers to be used as well as the degree of dropout preferred. A simplified prototype is presented with the epoch results from our initial testing shown. As the algorithm continued passing over the dataset, our loss graph witnessed a drop from around 1 to slightly below 0.6, whereas our accuracy witnessed a hike from 50% to 67.5%, and we're going to discuss this in detail today. We have also presented our initial results and an updated timeline in order to accommodate these recent changes and the progress we have achieved.
Good evening, everyone. It's Khloud M, and in this part we'll be talking about the datasets. To follow up on our research, we have searched for the newest credible datasets of chest X-ray from the last presentation in the past 3 months. A number of machine learning-based methodologies have been recently proposed for COVID-19 screening and X-ray scans as an efficient tool to help with the diagnosis. The added datasets are now defined if they are for positive cases, negative cases, or other lung diseases compared with the datasets in the very beginning once the virus has started to appear. They weren't organized or even titled or are messed up with COVID-19 cases, with non-COVID-19 cases, but recently different organizations started to get familiar with the patterns of lung lesions linked to COVID-19 more and more, and many people try to publish the most credible datasets to be used in the researches to help the researchers to find effective methodologies to detect the virus easily, as we are aiming to do in this project. We depended the most on the previous articles and related projects that were working in the same area to reach datasets used in the project, as we believe they should be trusted enough to be used, and it's already used in testing before in their projects. And so we searched for the latest articles as well to be up to date always, not only for the datasets but also for the algorithms. And we know that the dataset is a key for our projects, so the more datasets we get, the more accurate results we will obtain in the future. So we were searching in the published datasets, and we find some other that will help us in the future, and we will have a look shortly on them together in the coming slides. Now we have reached some problems related to the various datasets. We went through some problems regarding the datasets when we started to think about the implementation and have some real action. These problems are all the previous projects that worked in the same field hitting machine learning based methodologies and deep learning. They treat each X-ray scan slice independently, which means that the same patient may appear in the training and test set at the same time, which may produce misleading results. Second problem, the methods are trained and tested with sets of images from the same dataset. Third problem, we have some corrupted images between the datasets. Different datasets tend to present images of varying quality, which may come from different types of X-rays machines reflecting the conditions of the country's cities from where they come from. In order to address these problems, we consider them while inventing our algorithm, and we will be making checking stages for the datasets before starting the detection path to be filtering all the datasets that we have to eliminate any corrupted images. By now, we got around 7,000 images, and we will be keeping searching for more datasets to compare them for each other. Some works for testing and some for training and so on. So we don't rely on specific datasets. As we can see here, some examples for corrupted images, as we can see in the yellow circle in the right image and the red green squares in the other two images. They are examples for corrupted images that we will be misleading while trying to classify them. Here are some added data sets to be up to date. I didn't include the ones that I mentioned in the last presentation, just to show the new progress only here. Here are the links for the datasets. First one, it's a public dataset that contains in total 2,482 X-ray scans, some for positive cases like 1,252 X-rays and 1,230 X-ray scans for negative cases. I also included the detailed source for each dataset. Second one, the most special thing about it has more information about the patients, like age, gender, and some symptoms they might have. And in our application, we will be asking the user to add some symptoms, so this datasets will be very helpful for us for testing such a thing. The third one, it has 349 X-ray images, and the last two last updated were in April in the first wave of COVID-19, but we considered them also because they are really organized, and we search for more and more for data sets. These are some examples and samples from one of the data sets. And here also some examples of X-rays images that are some positive for COVID-19 and stop, and non-COVID-19 cases which are in the bottom. Here, we would like to give you a quick overview of how our application will look like. Here it's a basic homepage. If you are a user already, you need to click sign in. If you aren't, you have to sign up. As inputs, you have to input two important things, signs, symptoms you might have, and then just upload the image of your X-ray. And as outputs, you have to click detect, and then wait for the results. At this stage, I will let one of my colleagues to mention our algorithm in the coming slides.
Now, with our algorithm, we will first begin with semantic segmentation to crop the lungs area from the whole X-ray to guarantee better performance and accuracy. Then we will use image classification using our CNN to identify if the lungs are infected or not. We will begin with semantic segmentation. It will be based on convolution layers of size 3x3 matrices filters. Images before this step will be adjusted to 224 by 224. We will also use max pooling of 2x2 and stride of 2. We will use concatenation that will play a huge part on not losing features and getting back to the original size of the X-ray
We will use dropouts to eliminate overfitting, mostly 10 and 20%. There will be also a one-by-one convolution layer at the end to map each feature vector to the desired class.
Here is a diagram of our segmentation algorithm. We will input the 224 by 224 X-ray, then it will be convoluted twice with the 3 by 3 convolution matrices with 64 filters. Then it will be max pooled by the 2 by 2 matrices, and its size will be reduced to 112, and then it will also be convoluted twice with 128 filters. This process will be repeated 3 times till it reaches the bottom of 124 filters, and the left side is called contraction. From this part we will begin the deconvolution of 2 by 2 to get back to the original size of 224 by 224, and the right hand side path is called expansion, and here the contraction. The concatenation occurs as the last convoluted feature map from the fourth layer from the contraction side gets concatenated with the first from the expansion side to help in the localization of information and to not lose any feature, and then it will be convoluted twice with 3 by 3 matrices, and then it will be convoluted by a 2 by 2 matrices to get bigger in size, and this process will be repeated 3 times till it reaches its original size. Then the one-by-one convolution will occur before the output. And in this side, this is an example of a cropped long image, as the left-hand side is the original one and the right-hand side is the cropped long image. And now with the second part of our algorithm, image classification, and here we will be inputting the segmented pictures that will lead to higher accuracy. It will be composed of 23 layers, including input and output. We will use 3 by 3 convolution layers, 2 by 2 max pooling layers of stride 2, 3 dense layers of 4096 nodes, because of the huge number of parameters that will be 138 millions, and to guarantee that the voting will be as accurate as possible. And also we will also use a dropout of 25% to eliminate overfitting. The input layer in our CNN will get images of 224 by 224 and will consist of 3 channels, as it is RGB, not grayscale, as there is some blue color in the X-rays. We will also filter the datasets to get the posterior interior type, because this is the most suitable and appropriate one. And this is a diagram for the architecture of our CNN. It will begin with the input layer, then 2 convolution layers of 3 by 3 and 64 filters, then the max pooling of 2 by 2, then 3 by 3 layers, 3 by 3 convolution layers with 128 filters, and then max pooling. We used this method of several 3 by 3 convolution layers to increase non-linearity, which will increase the accuracy and clarity of the picture. And of course we are using the ReLU function with every convolution layer throughout the whole classification process. After the 3 by 3 layer, we will use 2 3 by 3 convolution layers of 256 filters, then max pool, and then we will max pool it, and then we will use 3 by 3 convolution layers and 1 max pooling layer twice with 512 and 1024 filters. Finally, we will use three 4096 node dense layers where the voting will happen, and here we will know if the X-ray is infected with coronavirus or not.
In the prototype, we started by importing the photos from the dataset. We chose a small dataset consisting of 746 images. We split it into two, 640 images for the training and 106 for the testing. The 640 images had positive cases and negative cases, as well as the 106 images. The model consisted of 4 different CNN layers, flat layers, dense layers, dropout, training, and testing section. I will be talking about them in details now. So in the model, we started by creating the first convolution layer. The first convolution layer had 32 filters. That was mainly made for the small parts to have to make small detections. Our kernel size was of size 3x3, which is the standard choice. We used the ReLU activation in all of the 4 layers and the same kernel size for all of the layers. And we specified that the input shape should be 224 by 224 by 3, meaning the height of 224, width of 224, and 3 different channels, number of channels. This is the standard choice. Why we chose the standard choice is that when we increase the size, it will make the training very difficult to make. And if we make the size smaller, we will miss lots of details, and this will affect our accuracy. After our first convolution layer, we created another convolution layer with 64 filters. We increased the filters while we're moving on in the model. However, we have the same kernel size and ReLU activation, as I mentioned. We added 2 layers of convolution network, 3x3, instead of having one 5x5, because of 2 main things. The first thing is that if we add 2 layers, this will increase the nonlinearity, which was what we need. And the second reason, it will reduce the number of parameters. For example, 3x3 and 3x3, this is 3 times 3 is 9, and 3 times 3 is 9, so 9 plus 9 is 18. However, 5 times 5 is 25, so here we have a reduction of the number of parameters. Moving on, we created a pooling layer, which we used the max pooling with the default size, which is 2x2. Then we had the dropout layer, which prevents overfitting, as we don't want our data to be overfitted or underfit. After that, we had our third convolution layer, which had 64 filters as well, and the same activation ReLU, and then max pooling as well, and the dropout. And finally, we had our last convolution layer, which had 128 filters, and the same max pooling and dropout as well. So all this was our model. Now moving on to the training part. What we did in the training part was that we used the gradient descent method and image classification. We started by rescaling our data. This will help us with the normalization. And we started by giving the training images to the machine to train on them, and then test them and to get our accuracy and loss. Moving on to the next slide, this is our results, what we have till now. We had 20 epochs, and each epoch consists of 10 steps per epoch. Moving on to the next slide, this is the loss graph. The loss graph shows that our loss decreases by the number of epochs. As the number of epochs increase, the loss decreases. The loss for the model to be perfect, it's preferably that the loss becomes 0. However, it's very difficult to have a loss of 0. And since we're just at the beginning and having this loss, I find it a very good start. The next graph is the accuracy graph. This accuracy shows that it ranges from 50 to 70, almost 70%. And I'll be talking more about our results in the upcoming slides. So moving on to the next slide. In this slide, we show that we got our highest accuracy of 67.5% in epoch 18, and our lowest loss was 58.16. 0.5816 in epoch 20. To our last slide regarding the prototype, which is our results from the prototype. We achieved an accuracy of 67.5%. This was our highest accuracy. However, the PCR has an accuracy of 66% in the late stages. This is its maximum accuracy, and 60% in the early stages. So this shows that our prototype has a higher accuracy than the PCR till now, and hopefully by the end of thesis 2 we'll have a very, very high accuracy, making it a more reliable source than the PCR.
For our process, so I'm going to start by a small outline for what we are going to do. First, I'm going to start by testing and documentation, and then we are going to talk about regulations and paperwork needed for our project. And then we're going to the third step, which is approval from doctors, and we will gonna end it by the distribution process itself. So for our testing our product, we will start by testing it among different data sets in order for us to get the best results. After that, we will start documenting our product for making it more understandable to people reviewing it. And then we are going to move for the second part, which is from our process, which is regulations and paperwork. We will start by going to the Ministry of Health and Population to demonstrate our project and offer it for them. Then, after presenting our product, we will give them all documents needed to understand it well and to be more professionally. After that, we will also show the importance of our product in helping to detect COVID-19 and decreasing the rate of expansion of the virus, and also decrease the time needed for the initial testing for any patient that carries the virus. After getting their initial approval, we will have to start looking for the paperwork needed for releasing our product and showing it to doctors. And this is a third part of our process. We will have to work hard in this part to persuade them to approve our product, as they do not trust any digital or machinerized way of testing any kind of symptoms for any patient to know their problems. They prefer face-to-face testing. And then for our last part of our process, we will look for the real distribution process. After getting approval from the Ministry of Health, doctors, and completing all needed paperwork of our product, we will start by distributing our product among hospitals that are deployed for the virus. Then we will go to public hospitals that need it to decrease the cost for our community members in the process of testing. Then we will go to the rest of hospitals and laboratories. At last, we will publish our product to any educational institute in order to improve our product, or even use it as a reference for any related product. And we will make sure that we will maintain our product in any hospitals or institution that we will deploy it inside it for maintenance when needed. For our time plan, we started in October where we studied different models like CNN image segmentation and image classification. We also studied the available data sets to know what model needed to implement and most suitable for our project. In November, we moved for looking for algorithm based on our study of the models and data sets, and creating a prototype, which we have done both of them. And in December, we are finalizing our prototype and our algorithm, and looking for ways to deciding the way of implementation. After that, for our this project part 2, which is CIS 2, we will start in Jan by collecting more X-rays and CTs from patients. Maybe we can use it manually or rely on other data sets that we can get. And in February and March, we will stick by our initial plan, which is coding and applying our algorithm. And in April and May, we will also do the same thing and for testing and presenting what we have accomplished in the end.
So, to conclude our final Thesis 1 presentation, we would like to recap our established progress. Firstly, we have allocated the datasets necessary for us to perform our initial testing on. The dataset imagery currently being employed is supposed to soon be replaced with actual CT scans that will be sent in to us by medical facilities. We have decided upon creating an application on the front-end side in order to ease the access and utility of our service. The application prototype and early design concepts have also been presented. Our implemented algorithm has demonstrated flexibility as it can be performed using 2 methods, and we now truly believe that we have outlined and refined the necessary procedure for us to deploy our project. With this being said, we satisfyingly fully conclude our research phase and set our sights on completing the upcoming implementation phase ahead of us. Thank you for listening. Here are our listed references, and we are open to any questions.